Okay. As usual, we'll get to, or as previously, after today becomes usual, now that we have a pattern, we'll go over the test at the end of class. All right, so we were talking about AVL trees last. Any questions on AVL trees at the moment? We'll do a couple more examples. Just to see that it is sinking in. All right, take it there are no questions then. We're ready to build some more trees. See if we can't make a forest. All right, first data point becomes the root. It's a binary search tree, so we'll go ahead and build off the root. The new data points as they come along. Every time we insert, check for balance. If we're out of balance, then we need to do the appropriate number of rotations, that being 1 or 2 rotations. All right, after we add 30, we're going to find ourselves to be out of balance. The 20, 30 subtrees, all right. All right, 2 nodes, it's either be one on the right or one on the left. There's not much else we can do there, but we've got 3 levels. Number of levels on the left-hand side versus the number of levels on the right-hand side, or the height of the left-hand side versus the height on the right-hand side. Says we have a problem since we inserted right into the right side, right, we went right, and we went right. Again, adding 30 to the tree. We're doing a single rotation of our beta node towards our alpha node. Once we've done that single rotation, we will be good to go. So 20 pulls up. That causes 30 to come along with. And we're back to balance. And of course, double check, make sure you have a binary search tree. If you don't have a binary search tree, then something has gone wrong. All right, all my data is just in a nice ascending order. So we're just going to get the same story happening right all over again. And here we have no alterations we can make to this tree. Each level of the tree is full until we got to the leaf level, and there aren't any levels below that. So this tree is going to be as balanced as it can be. But as we keep on growing, we'll build some imbalance. All right, so again, as we had before, .30 is going to be our alpha node. The height of our subtrees exceeds our max distance of 1. And since we went into the right side, and then again the right side, it's going to be a single rotation, right? Beta will move up towards alpha. And our single rotation will be good to go. All right, 40 is moving up, 30 is going down. And we need to fix our links. And it's still a binary search tree. Get a little tight on space here. See if we might squeeze it in or not. Yeah, I think go another. Drawing. Got all the digital white space we need, right? So might as well leverage it. Last data point. Bring 60 into the mix. All right, and we need to check our heights. All right, here we have our first subtree. All right, 2 nodes, as good as we're going to be able to make it. Like the 40 node, right? 1 level, 2 levels, that's as good as we can make it. And then we get to our top level. At 1 level versus 3 levels, or a height of 0 versus 2. So alpha will present itself. We went into right and right again. Still another single rotation. Beta towards alpha. So the entire tree is going to move up. All right, and we're going to have left subtree falling off. So I'll set that aside for a moment. 20 moves down, we'll fix this link. And remember, like before, 20 had 40 as its right subtree, so its right subtree is available to take on ownership of the left subtree that 40 had previously. And our tree is as balanced as we're going to get it. How are we doing with our AVLs? Right, so I'll just leave more or less some exercises for you to build out the trees. Effectively the same data, but when you change the order, it alters the nature in which it grows. See some code? I don't have any code myself, like Geeks for Geeks does, so we can go take a look at it. Really? I got to sign in. All right, scroll till we get to the code. Ignore all the ads. Perfect. Let's unpause the ad block for now. All right. Right, so node definition, just like before they're adding in height. Characteristic there, which of course would be helpful. In tracking heights, when you're asking how tall are my subtrees, they can just immediately report back what their heights are, and then if there's a rebalance, adjust the heights at that time, because after you add someone, that's going to affect the heights. Right, the getter for height, nothing special there. Max helper function, new node, right? That's what they call a factory method. Its job is to generate or create nodes. So a helper function, it's here, might as well talk about it. Pass the key in, it just does all the default stuff. So let's add a detail of adding the height. All right, so you can see they're going the zero-based height system here, where a leaf being added, the height of that subtree is a 1. So if we wanted it to be a -1 based system, this would be a 0. And there's not much code difference between -1 versus 0 based empty tree heights. Technically just one hard-coded constant. And what they have there, a couple of rotate functions. All right, pass the node in. And it's basically just pointer maintenance, just like with our linked list classes. When we're bridging things in, we need to go ahead and keep track of, yeah, it's similar to a constructor, but it's not, because we're inside the tree class. What they call the class? Well, they're not even doing, they're doing global functions. So never mind, they didn't actually put this, they didn't object orient it. It's just, yeah, so it's not a constructor because it's not actually inside of the node definition. So yeah, it's effectively like a constructor. They just didn't make it as a constructor, which yeah, that's a way to go. Object-oriented coding is a more common way of going, but that does, I suppose, help keep things a little bit simpler. Right, returning back our node star. So keeping track of the area of the tree that we're in. And then they are doing some height maintenance, right? That, so we catch that. So let's draw some tree. So rotate right. So I'm going to assume we're at this state. Let's see. So this is Y. This is X as Y left. And T2 is X right. So that would be null. X right equals Y. So you can see they set T2 aside in case there's a subtree here to keep track of, as we saw in the previous example, so that we can track it later and reattach it. X right equals Y. All right, so X right equals Y changes. This moves us up. All right, so now X is over here, and now we're saying Y is its child, and then this node just gets carried along. Let's call this one Q. It's outside of what we care about. So X, oops, back to my mouse, right? X right equals Y. Made our first link change. So that was a carry through link. And here's our updated link, right? Because this link was tracking T2 before, it happened to be null. So we're overwriting something that wasn't actually there. And then we have y left equals t2, right? T2 is null. So we're just setting y left equal to null. Otherwise, we would have been copying over whatever may have been in this T2 tree, if there was a T2 tree. And then they did some height adjustments. Yeah, because heights changed. And you can see we got some recursion going on here. Heights calling heights because everyone in this branch just got shorter. Everyone in this branch just got higher. So all kinds of fun maintenance when you jangle a tree up a bit. Is everyone okay with the rotate right function? All right, node y would represent alpha, x is representing beta, right? Alpha and beta are just arbitrary names. Just the names that we're using. Is an AVL the most common type of tree? Well, I'm going to say, I don't know. Database is going to be using the next tree type that we're going to be talking about tonight, which is B trees for indexes. I would say an n-ary tree is going to be the most common tree type because like a folder system, that's an n-ary tree stuff where C is the root of the tree, and then all the folders you have at that first level, right? Program files, system, whatever there, those are then roots of their respective trees. Websites, right? The HTML that represents this, you'll have body as the root of the tree. Then you have a bunch of children, so that's gonna be an n-ary tree as well. And then those children can have children. Lots of HTML's container types are, and not most, many of them are container types. And then forms applications, it's a very similar model where you have the page is the main control type, and it's got a control collection, which is a list. And then those controls that are container types can then have lists of controls. And they'll also be n-ary trees. So not knowing the whole world, I'm going to speculate and say an n-ary tree is the most commonly used tree structure. But like a lot of the things we look in this class, there are specific areas, there's very specific areas of applications for the various tree types that they get used. One second. Okay. Here are my drawings. I think they're going to have a similar one for rotate left. Yeah. Or left, right, rotate, left, rotate. You can see the code is pretty much the same. Who we are grabbing is tweaked a little bit. And there's a logic in here somewhere. Yeah, here we go. That handles our cases for knowing we need to do our rotations. All right, so here we have our two single rotations. Return a right rotate or return a left rotate. Otherwise, I'm doing a left rotate followed by a right rotate, or the reverse, a rotate followed by a left rotate. I believe that's about it. Traversal, main, yep, okay. All right, and you see they're talking about H. H is in terms of n log n, or excuse me, log n, as they are erased. Well, we don't get into the red black tree. It's one of the other similar ones. We can't, not enough time to get through them all. Try to get through as many as we can. So the next one that we're going to get into. Let me post the link for this. Since you asked for the code, I'll mention it there. There we go. All right. No problem. We're 312. B trees. A B tree. Note, B does not mean binary. In fact, has no meaning or has no name or expansion, whatever you want to call it. This is also a self-bouncing tree structure. It is going to be built bottom up, right? Unlike several of our other trees, it is going to be specified as an NM tree where N represents minimum number of children and M specifies maximum number of children that a node can hold. All right, so a 2-3 tree, all right, we're saying a 2-3 B tree, same difference. Allows 2 or 3 children for a non-leaf node. It is similar to a binary search tree in that we have a left to right ordering mechanism. But instead of 2 ranges per node, we'll have as many as M ranges. Whatever the max number of children is. There will be a number of data points in the node definition. Total number being 1 less than M. All right, so for a 2-3 node structure, I'm going to have an array data points. Length 2. And an array of pointers. So we have a length of 3. So if we go ahead and draw this. We have 5 fields inside. Link 0, data 0, link 1, data 1, and link 2. All right, so here, separating in 3 parts. Link 0 points to the subtree, which contains values less than data 0. Link 1 points to the subtree, which contains values less than data 1 and correspondingly greater than data 0. And link 2 points to the subtree, which contains values greater than data 1. Right, so just like a binary search tree would just be this part of the structure. All right, so our next iteration is to add one more dividing data point, and one extra dividing data point gives us one extra branch. All right, so building a tree, we'd have binary search trees still going to start from the root and work our way down to a leaf. Once we're at a leaf, we'll add the value into that leaf. If there isn't room for the new data point, we'll split that node and promote median value up the tree. If we split the root, a new root will be created, joining together the old root and the new node that's split from it. All right, so we're going to simplify the way we draw the nodes. 2 boxes where the edges of the boxes are the data points. So our data 10, 20, 30, 40, 50. We'll just go straight up the ladder. For our first example, all right, so our first insert, there is no node at the root, so we'll go ahead and create our root node and drop the data point in, and then we're done. 20 comes along. We find a leaf. That leaf has room in it, so go ahead and drop that data point in there. And we can move along. Next up, we'll have 30. Do not have room for 30 in the tree. So what we'll do is we'll create a new node. The rightmost value goes into the new node. The leftmost value will stay where it is. The median value will get promoted up the tree. And since we we split the root, new roots forming, and it gets promoted up. All right, so it looks very much like a binary search tree at this point. As data comes in, we'll be comparing just like we're doing with binary search tree. All right, so 40 comes along, compare to see which way to go, because this is not a leaf. So now we're gonna have to dig for a leaf. 40 compares to 20, sees it's greater than 20, looks to see if it's less than or greater than the second data point. There is not a second data point, so it goes in, moves down to the 30 node. 30 node has space for 40, so we can go ahead and just drop it right in. And that one's done. Next up, we have 50, just like before. Compare to the root, find a leaf, see that that leaf is already at capacity. Rightmost value, which happens to be the new data point, is going to be pushed over into the new node with 40 working its way up the tree. There's room for 40 up the tree, so it'll go ahead and fit into that node. Now it's just a matter of adding a link. Right, so right now, if we look at our data, 20, all values less than 20 in the first subtree, 2040, all the values between 2040, second subtree. And then we have our 50 subtree over here, waiting to go ahead and be linked in. So we've dropped that in and we can carry on. Okay. 60's up. Not less than 20 and not less than 40. So we go to the third branch, find the leaf has space, and we're done. 70's last up. Not less than 20, not less than 40. Third branch, no space. So we'll create a node for it. Drop the rightmost value or the largest value over there. And 60 is moving its way up. All right, so 60 working its way up the tree. But it is also finding that there isn't space. So what we're gonna have to do is split this node because 60 does not have room for it. The rightmost value goes into the new node with the middle value being promoted up. And before we go ahead and carry that value up, go ahead and let's fix our links. And you. Right, so 60's moving up and got tossed into a new node. We want to go ahead and grab the previously generated new node. So it's quite possible several new nodes created for a single insert as the splitting works its way up the tree. 40 is going to be moving up. And as it does that, this link will want to move over so that our 60 data point is splitting its two subtrees. All right, so now we can go ahead and have 40 move up. And since it was a root that we're splitting, a new root will form, value that moved its way up. And it will point to the former root in the newly created node that was created at the previous level. All right, so key thing I want to point out and type out here, a node has one data point and it has two children. Let me further qualify that. If an internal node has two data points, then it has three children. And there's no other possible state that the B tree can be in and still be a B tree, where we can't have there not be this child node. We can't have a 60 node with just one branch. It goes against the definition of the data structure. If a node is internal, it should be everything above the leaf level. And so this is our internal layers tree. If we have one data point, then there must be two children. One data point must be two children. One data point must be two children. As we start to fill with greater data, then we might have three children. So we'll go ahead and keep building this tree. All right, we'll add. All right, so these are for okay. B trees are used by SQL Server for non-clustered indexes. All right, so a clustered index is a data layer that's on top of a data table. And so, for example, say we have a database of users, whatever, users. Internally, they have a user ID, and that's the primary key. Yeah, this is what I was doing most of my database table design. It's so tedious sometimes. Anyways, primary key of the table. So if we want to look up user by their ID, is a fast operation because binary search, basically, is the smallest. ID is furthest left, and largest is furthest right. All right, but when we're logging in, probably using a username, such as gcuevas. Right, so if don't have any non-clustered indexes, we have to do search against the table, find my hashed password, etc., whatever it is that is in this database that I'm logging into. So that's going to be terrible performance, and we don't like terrible performance. We like things to be fast, especially as users. We have a strong preference for things being fast over slow as a general practice. So what we can do is we can build a heap on username. Not a heap, build a tree, or build an unclustered index on username so that looking up the data is much faster, right? There you go, login time, since it's a balance. Since a B tree is balanced, right? 100 million. What is that? Millions 20. So it's 27 levels of tree. That's if it's binary. That's, of course, the heaps they're using are not going to be binary. SQL Server does is based on their internal page size and how big the records are, how many things are in that unclustered index, because you can cover some of the fields as well. It's going to have the NM be determined based off of that particular index that it's building. And that sits on top of the table, and basically the leaf level is saying where in the file system the data is, so that we can go look up whatever data that we need is being stored on the file system when someone logs in. All right, yeah, and looking at 27 layers at the worst, as opposed to 50 million on average, definitely gonna be better. And as you're working in large data systems are gonna be even much more crucial that the data has, this is metadata, effectively data about data in a way that we can do things quickly. All right, so this is the most common usage. So if you actually take I forget which SQL class it is, but SQL classes will get into greater detail to these. We're doing a little bit of a simplification or simplified version of B trees because we're only just focusing on the key data. They'll get in real deeper and so you actually see the record sets and all that fun stuff. That is beyond our scope. Let's see, did I still have that in yesterday? All right, we're going to go ahead and add 35 and 32. 35, less than 40. Go left, not a leaf. So we do our data comparisons and we find, we're gonna go this way. And once we find a leaf, drop it in and we're good to go. Like before, start at the root, data compare, find our leaf. This leaf does not have room. So what we're gonna have to do is split this. $32 is the median value. It's moving up the tree. 35 gets over to our new node. 32 is promoted up to the 20 node. There is space for 32. So we're going to go ahead and drop it in. And then go ahead and link up our nodes. Now we have a 2 data point node, and that node has 3 children. Okay, add 15 and 5 to the following 3 tree. 15, start at the root. All right, do our data comparisons. 15 is less than 40, it's less than 20. Find a leaf, drop the data in, and we're good to go. Next up, 5, less than 40, less than 20, found the leaf. Do not have room for it. So we're going to have to split. Smallest data point is staying. In fact, let me draw this correctly. All right, so 5 stays in our existing node, and 10 is working its way up. All right, so we have 10 working its way up the tree. We see that there is not space for this data point. So we're going to have to split the node. All right, so as a temporary or as a visualization aid, 10, 20, 32 is what we're trying to create. But we're constrained to a 2, 3 node. So what we're going to do is 10 stays in the already existing node. 32 gets pushed over into a new node, and 20 is working its way up the tree. All right, so 10 is the existing node, and it's pointing to our existing leaf node. 15 was our newly created node at the leaf level, and we want to go ahead and link that in. So we have, right, just look at this part of the B tree. Single data point, 2 children, less than and greater than that single data point. All right, 20 is working its way up. All right, so 20 is working its way up. Tree, notice that these links, all right, pulled them over, then shift them to make sure that we're good from this perspective. And we have 20 working its way up. When we get to the root, we see that there is space for 20. What we do is shift the second pointer over to the 3rd position, in addition to shifting 20 over. Same thing, the other link that is going to shift over and link to our newly created node. All right, so let me add some color here. All right, these nodes just came into being in the tree. All right, so before the addition, we had 5 leaves. Now we're up to 6. We had 2 nodes at the 2nd level. Now we have 3. And we still have the single root. Two nodes were added. If we were at capacity in the root like we are now, that would have also split, and an additional node would have been created for that level, and then an additional root would have come along and replaced that. At this point, we have quite a few data points to add before we can get there. Even before creating new nodes, we have 1, 2, 3, 4, 5, 6 available positions, and each node in this 2nd level has room for an entire new node underneath it, which is an additional 2 data points per. So we have 12 data points that we could craft to fit in here before we get to the point of causing this to split. But if we keep, say we get a bunch of large values coming along, right, 80, 90, 80 fits in, 90 causes 80 to move up. And then we have a couple empty spots. So I push through 55, 56. All right, 56 goes in new, 59 pushes up, causes this to split, causes 60 to push up, causes this split, and 40 ends up in the root. So it's possible that we might have more data to one side or the other, but the number of nodes are going to be consistent, and each layer is growing by a factor of 2 or 3. Okay, let's go and take a 5-minute break. Let's try to absorb some of that and then do a couple more examples. Let's take 5, go on mute. All right. Let's keep on building. First data point drops into the first position. 51 comes along. That is going to push 55 to the right. Remember, we have a data relation. The data within the nodes do need to be ordered because we have a less than, in between, and greater than growth pattern. So I can't have 55 for 51 because then the data relation does not line up. 38 comes along. Pushes 51 out or promotes it. 55 gets pushed out to a new node. And our new root takes 51, 51 being the median value. What we have there. So real quick with me so far and what we have with our 2-3 tree. Okay, 32 comes along. All right, less than 51. Finds a leaf. Pushes 38 over. Drops the data point in. And then 28 comes along. All right, pushes values out. New node takes the largest value. Middle value, 32, promotes up. And 28 stays in the already existing node. All right, so 32 moves up. That is less than 51. So 51 will move over. Pushing that link along with it. And since we came up from the left branch, the left edge stays where it is. 32 drops in and will link to the newly created node. All right, so depending on which branch we're promoting up the tree, it's going to drive which links might need to get pushed around. But that's our growth pattern. So at this point, if I add 2 values that are less than 32, that'll push one of those values up the tree and 32 will become the new root. If I push 2 values between 32 and 51, they end up in this subtree. One of those values gets pushed up and sits in the median, it'll get pushed up again and become the new root. I'm going to push 2 values that are greater than 51. And whatever values there are going to be there, they're larger than 51, so they'll come up here, be pushed over to a new node, right? And 51 will become the new root. So it's possible for any value that's in the tree to become a root at some point, not necessarily on the next addition, but it's possible for any value, right? Because 28 could get promoted up. It wouldn't become the root at that point because 32 would be, but it has the potential for working its way up. In general, the middle branch is more likely to have candidates that are going to become the root because just the natural balance of things, middle values are going to be working better as dividing the data, just inherently by the way the tree grows. So those middle values are going to keep pushing. Where if we keep dumping much of smaller numbers into this tree, right, they'll work their way up, but that's the median is just pushing over that way, right? If I keep adding values less than 30, The median is just pushing further this way as well. Just changing what's relatively median in that data set as we grow the data. All right, so let's build another one, this time pushing middle values. Pushing values into the middle. Okay. $10, $50, $30, $20, $40, $35, $32. That'll probably be good enough. Thinking too far ahead. So first data point is our root. Then we have our 1050. Then 30 comes along. 50 jumps to the side with 30 coming our first promoted root. All right, 20 comes along, less than 30, greater than 10, and we have space for it in that leaf. 40 comes along, greater than 30. We have room in this leaf, so push 50 aside. Let's see, and then we have 35, right? 35 greater than 30, less than 40. So we'll need to go ahead and create a node. Push 50 on over into that. 40 is promoting up. And we'll link together. Let's see, looks like I need to do one more value. Beyond our last data point of 32, right? 32 is in between range. Pushes 35 to the side since we have room for it in our leaf. And we'll add 38 to our data list. All right, so take a look at this last value. This last value is going down the middle branch. So that means one of these values, since we're going to be overflowing, this node is going to promote up. Whatever value it is that promotes up is going to be the median value between 30 and 40 and is going to become the root. So if we push a value between 30 and 32, 31, 31 and a half, whatever, then 32 would become the root between these two numbers. Then that new data point would become a root. Greater than 35, less than 40, as we have here, means 35 becomes the root. So 38 comes along. Don't have room in the leaf node, so a new node is created. The median value is pushing its way up. There's no room for 35 in here. So we're going to have to create a new node. The rightmost value will be 40. And 35 is going to be working its way up. All right, so as we shift our values around, we will adjust our links. And 35 becomes our new root value. Okay, so our internal nodes all have one data point. So each have two children. So this one node over here, it's almost just a binary search tree. All right, so it's largely similar to a binary search tree, except nodes get created on the leaf level and also in the internal levels as we build the tree. So that's the key difference between a binary search tree and our B trees. We don't add to the bottom of the tree, we'll add at the bottom level and possibly also push up nodes in the core structure. If the tree is getting taller, it gets taller because a new root was created. Whereas with a regular binary search tree, the first node is the root and stays the root forever unless you change it over to an AVL or something like that and gets rotated to one side or the other. All right. We'll not be doing code for this one on the test, but we can pop something up here. Good Geeks for Geeks. Good site. So I just want to point you to it, but not going to see this kind of code on the test. When you get into a file structures class, that's one of the places where you'll likely have to implement this, but let's go over it really quickly here. Yeah, they're sneaking their ads past the ad blocker. Clever. Anyways, right, two arrays for our fields, our key, our structural fields. And as you can see, that, like I mentioned in the notes, there are one fewer data points than there are children. So we've got an array of nodes and an array of data points as usual. Right, keeping things simple, int. I'm not a big fan of saying int for a Boolean, but it'd be the only Boolean here, so it doesn't much matter for the structure, the size of the node. And they are doing a back pointer for the parent. All right, since we are going to be working our way back up the tree, if you're not going to keep track of who the parent was with the stack, then this is one of the other ways you can keep track of things with your parent with a linked-based structure. Or when we have our array-based tree structures, we don't have to worry about links because we cover that with our math. But when we're links, we're very, very restricted on where we can go. All right, so search for leaf, this should be their insert. I assume going down, figuring out which way to go. Right, really going down the first branch, or we're iterating down, looking for the branch that we want to go down. Oops. Horizontal scrolling. Horizontal scrolling is bad, 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 bad. And I've got no scroll bar here. So where is the scroll bar? There you are. Okay, find where we were. All right, so recursion always our fun friend. When we have nonlinear structures, I don't recommend. Yeah, this is problem on websites, right? Bars, ads, eating up our menus, eating up our screen space here. I don't recommend using recursion when you're dealing with a single branch, right? A branch is effectively a line in the tree, right? It's a path. That path might be a very jagged line going left, right, left, right, left, right, left, right, but it is a line. So for something like that, I recommend not doing recursion because recursion probably isn't going to be buying you anything there. We just iterate through and just create pointers, we trailing pointer and just iterate down, going down first, second, fifth branch, whichever branch as is necessary. and just change who we're iterating on. But there's always more than one way to go about it. All right, so let's see here. Where are we going up our parent? All right, so hit the capacity, and there's going to our parent. All right, so we're checking that there is a parent, and code scrolling off the screen. Yeah, so this is more complicated than we're going to get to in this class. So you can see there's quite a bit of code going on here, and there's also, let's see, is this one doing borrowing? Instead of splitting, one of the things we could do, right, say we wanted to add 5 into this node. And we want to add 5 over here. Well, instead of doing a split, what we do is promote 20 and push 30 over here and then 32 over there. And so we get 5, 10 moved over, and we've got 20 up here. And so we make use of the available space. So this saves us from having to do splits. So that's one of the things that full implementation of B-tree is going to do. And then deleting would be the same idea, or the reverse when we're deleting, right? If we're getting to the point where I don't have enough data to have enough children for it, we can go start collapsing, and then it's, you know, a fair amount of collapsing has to go on there. So it'll do a similar approach where we borrow, right? So if we deleted, let's clear that. So if we come along and we deleted 10, we're okay, but then we say, well, and let's add a data point over here, 34. And let's just go from the other side, right? So say we want to delete 32, right? If we're just doing the full reversal where we're just going to start collapsing things down, we can collapse this tree, right? Because we're getting down to 1, 2, 3, 4, 5, 6, 7 data points. 7 data points can be handled, right, with a 2-level tree, right? Because we can get 2, 4, 6 at this level, plus 2 splitting, right? So we even have 1 spot available. So we're down to 7 data points. We couldn't collapse the tree. The tree is just going to grow back up again. We can do the same thing as we were just talking about by shifting values around. Just move 30. 32 was, then 20 comes up here. And we keep the structure it is. We're just shifting a few values around. And it is, of course, going to be a little bit easier to shift a few values around instead of collapsing the tree structure. But there's only so much shifting you can get to before you're going to have to collapse. And that's an even more complicated scenario. So we're going to cut it short there. Say that if you go take a file, structures course, and get to implement this stuff against the file system. And that's about it. Let's see. Any quick questions about the program that was due last night? I see most everyone has it turned in. So a few people straggling. We'll go over this one next time. For those of you who haven't turned in, what might you be stuck on? Any questions here before we talk about program 3? Okay, program 3 is just a binary search tree where break statements required. Which depends on how you coded it. So no. But I'm not sure what you mean by break statements. But if you're doing a switch, you want to use breaks. You want to do you're looping that's terminating early. You want to use break keyword in that. It just depends on how you code it. Okay. That's not what I meant to pull up. I meant to pull up program 3, not test 3. Early preview of test 3. Okay. Program 3. Just a binary search tree, link based. And we'll just dump 15 data records in it. And 15 is just arbitrary numbers, just trying to exercise all the different ways that the data might want to end up. Key data is going to be the name, all right, and the weight is just the secondary data point. Various traversals, all right, these are pretty easy. We've done these, some of these in the labs. Let's carry them over. Tree height, right, using recursion. All right, so, right, what's the height of this tree? I'm gonna write the code. In fact, what's the height of an empty tree? I'm gonna write the code starting from the base case, right? Because we're using recursion. So when you're writing a recursive function, you want to start from the base case. All right, so if we have some sort of height function, right, could just do something like this where we check the root of the tree. All right, if that's null, return -1. Otherwise, going up and then calculating our way along the line. So what is the height? Ooh, something I meant to do. Wanted the eraser. All right, what's the height of this particular tree? We start at the root. In order to determine the height of our tree, we have to ask how long or how tall is the branch on the left side? How tall is the branch on the right side, right? So if the left side comes back and says -1, come back here, ask the same questions, right? Asks its subtrees how tall they are. -1, -1. The height of this subtree is going to be the max of these two numbers. Then we add one for itself. So it's going to say my height is 0. So we get to the root here. It's going to ask what's the max of these two numbers. Right? 0 is the max of those two numbers. Add one for ourselves and say my height is 1. All right, so you just need to get the left height, get the right height, and then just do a comparison on those two data points. Whichever's larger, add one to it and send that back to your caller. Does that kind of make sense? Okay. Leaves. All right. How do we know how many leaves a tree has? So we need to ask the question, how do we programmatically tell that a node's a leaf? All right, so if a node has no children, then it is a leaf. And we can compare, say if left is null and right is null, it's a leaf. If they're both null, then that's null is null. Null is equal to null. So we can simplify that test just by comparing the two against each other, since the left tree can't be the same node as the right tree. So these can't logically be equal and mean something else. And we're a leaf. All right, so that's effectively our base case. Got down to a leaf level. Otherwise, we need to get our left count, get our right count, and then send back the sum of those two numbers. All right, so say we have a tree like we had before. Goes left. All right, you want to do your null checks, of course, wherever you want to do them. So turns back 0. There are no leaves in this empty subtree. Go right, comes here, says I'm a leaf. Sends back there's 1. And 0 plus 1 says there's 1 leaf in this whole tree. Right, if we have a larger tree, same thing, go left. This comes back and says 1, go right. Right, 0 here, 1 here, so returns back 1. 1 plus 1 gives us 2 leaves in the entire tree. All right, so the recursion is very similar to the traversal recursion. You're just doing different analysis and slightly different base cases for what we're doing for getting the height and getting the number of leaves. Search, and that's just a lookup, go left or right based off the name. And make sure you account for it not being there. Lowest weight, right? So this is also going to be a traversal because we're not keyed off of weight. The lowest weight can be anywhere, right? If we have Mike at the root, Kathy over here, Tom over there. All right, let's say Tom's 111 pounds. Kathy's 114 pounds, and Mike is whatever, 200 pounds. Right, the smallest data point can be anywhere. So basically, go to the root, grab that value, and ask if the left side has a smaller value or the right side has a smaller value. And now you're just taking mins. Right, so the height you're taking maxes, for the returns here you're taking the min. So it's very similar code to what you're doing to the height. This time we're not testing for release, we're just actually inspecting data, the data in the node, and then deciding which value to pass up. So when we come here, there's nothing to pass up, so we send 114 up there, 111 passes up there, we take the min of those 3 values, and then the 111 is our smallest data point. Find the first name in alphabetical order, right? There is a predefined position where the lowest name can be. So you can go ahead and just dig straight to it. Right, EXE, you don't need that if you're on apples. EXEs are optional, doesn't much matter. I'll throw it in OnlineDB to test it anyways. Make sure that link's good. Tree state, all right. All right, that's due on the 26th. Talking about the 26th. Right. Right, so you'll have the whole week off. That's spring break, so we have one more lecture before we jump into spring break. That's where we are so far. Any questions about program 3? All right, let's go over the test then. Oh, no, got to. Let me pause so I don't goof. And let's stop the recording. So in case I double goof, I will